Good morning, everybody. My name is Ryan Morris. I'm the Market Product Manager with SICK for our machine vision portfolio. Today we are coming to you with a focus on some of the applications and touch points, specifically around our tire industry. Some of the applications that we've been seeing, the technologies that we're applying, specifically around our 3D and 2D machine vision portfolio. SICK has been around for 75 plus years. Very well known for our photoelectrics and our safety products. But today, again, being the product manager for vision, I'm really going to focus in on what we've had for vision, how we can solve applications with both 3D and 2D machine vision in the different assembly processes throughout the tire industry. So with that, I'm going to kind of jump into a brief little presentation. We'll kind of show some of the imagery that we're able to collect with our 3D imagery cameras. And then also kind of maybe jump into what our 2D cameras might look like as well to do some of those tougher inspections that we might be looking at with tire. So as you can see, I have a few different products in front of me right now. From our Tri-Spector portfolio here, which is a ease of use 3D triangulation camera. Has a nice configurable GUI tool set built behind it with some nice factory calibrated data. A very, very intuitive device when we start talking about 3D vision. A little slow on the slower side as far relatively to the guys on the right here. But a nice simple user interface to be able to do some basic 3D inspections that we might be looking at in tire. We really focus on 3D here because as we think about tire, we think about matte black, we think about low contrast, and that's where we start to see a lot of the 3D power being a little more agnostic as we start talking about contrasts and lighting. That matte material can be very, very difficult to inspect with 2D. So 3D provides a nice little benefit of being able to provide height map profiles and be able to do analysis based off of the true 3D shape of the device. And the Tri-Spector is a nice little workhorse for that entry-level ease of use product where we're starting to look for maybe gross dimensional applications or gross defect analysis. Jumping to our right here to the higher end, we can see our Ruler 3000 portfolio, which is a nice calibrated assembly that we see here, and our Ranger 3. So the Ranger 3 is basically just a standalone version of the Ruler here. So the Ruler actually has this camera or this sensor inside, but just provides a nice calibrated field that we don't have to worry about external components, whether it's lasers or having a fixed geometry that we have to do with the Ranger 3. So nice thing about the Ruler Ranger combo here is they are very high resolution, very high speed, up to about 46,000 scans a second. So it's very very good for these sub-millimeter micron level type inspections if we're starting to look at tread analysis or splice inspections or high-end dimensional accuracies. That's where we'd start to look at our Ranger Ruler portfolio to do some of these inspections. The Ruler, again, as I mentioned, is just basically a calibrated Ranger 3 with some defined field of view. So we do have more of this, the one Ruler variant here. We have about 6 different field of view variants depending on required resolutions and field of views, but we are able to actually scale that whole portfolio with the Ruler family. Now the Ranger 3, we have a little more flexibility in this sense where we can actually bring in an external laser line and actually define our geometry to exactly how we want it for the application. But again, same sensor, same chipset that's in the Ranger 3 that you see in the Ruler, so you get that high speed, high resolution performance out of both of those devices. As we actually dive through the actual processes of building a tire, we do see a lot of touch points where we would have opportunities to be able to solve the applications throughout the assembly process. From the color line to the cutting and splicing of the tires to the assembly to the finished tire, whether it's dot code verification or just a general sense of like, hey, is this tire still good? And then we can maybe have the opportunity to maybe throw in some of the 2D cameras here as well, which we actually show here for final verification, whether it's for the track and trace of it, for the dot code reading, for any kind of barcode reading or assembly of the final tire there. So as we dive into what we kind of expect out of seeing with the ruler platform or the applications that we see, we can see a lot of the splice and dog ear inspections that we have for the ruler. So as we look at a tire, it's obviously very matte black. Trying to get a 2D imagery of an overlay of black on black is going to be very, very difficult to monitor and inspect that splice, that we have enough of a splice there. So with the 3D solution, as I mentioned before, being color and contrast agnostic, we're actually taking that a laser line projector to actually record the profiles of what we're actually seeing in the imagery itself. So with that, it's a lot easier to find that actual splice and that edge and be able to do a measurement based off of it. So you can kind of see in these images here how well and defined those splices actually look. Going further, we have some positioning and component tolerances and dimensional accuracies that we're looking for as well. Again, same concept with using our 3D triangulation cameras, whether it's again a tri-spectra or a ruler product, able to actually take that low contrast tire and actually start to find edges and get high resolution dimensional accuracies there too. So as I mentioned, the ruler, we can do scans up to 46,000 scans a second to sub-micron level resolutions in your height, but even getting your dimensional tolerances in your widths and your lengths, you're getting about 3,200 pixel profiles per image. So you got quite a bit of dimensional tolerances there that you're able to get some high component accuracies there for tolerances. Further, we have profile monitoring. Obviously, as the triangulation cameras are building up these 3D profiles, we can actually just start to do some analysis on the profiles themselves. What's the slope, what's the contours. So a lot of higher end dimensional stuff that would be a lot more difficult to do in the 2D sense, because you're talking about external lighting and trying to pull out profiles would be a lot more difficult in the 2D world compared to the 3D. So we're really starting to get into the power of 3D in tire manufacturing and assembly, because of that low contrast, because of the high tolerances and measurements that are needed. Even going into the sidewall inspection or the tread inspection, making sure the depths are right, making sure there's no foreign objects stuck in the treads, or just making sure that the actual tread might be the exact tread that we're looking for. That might be a good AI application, right, where we're sort of talking about 2D, like is it the right tread type? But 3D, very, very powerful and being able to build up those images. And I have some nice example images I can show here too, minus the little animations here. So we'll show some real scans of what these treads and sidewalls might look like. And again, tread monitoring as well. And finally, I know there's some traceability aspects to it. There's dot codes, and it's always a challenge to be able to want to read these. So 3D, we're also able to actually extract the surface extraction of the tire itself. So we're able to pull out those details as far as what the dot code is and start to apply some OCR algorithms to be able to read the dot codes. So we're able to extract a lot of that 2D imagery and 3D data in a single scan with the Ranger product, the Ranger and Ruler product here as well. So some very high-end capabilities that we're able to do with the sidewall and the OCR traceability aspect of things. We kind of jump right into the sidewall here. So these are some real scans that the Ruler was able to take, and you can see the level of extraction and detail that we're able to actually pull out with the Ruler product itself. So as I talk about micron level resolutions, this is kind of what I'm alluding to here. Be able to still see a lot of that print, a lot of that text, even in that low contrast black tire, still be able to pick up very fine level details in the sidewall there. As we jump into other components of the tire, we can, as I mentioned, we have varying field of views of our ruler product. So that sidewall might be more in line with like our ruler 3020 device, for a medium-sized field of view. But then we have our 3060 and our 3120 devices here as well. That can get you out to about 1.6 meters in field of view coverage. So as we start to look at a full tire scan, we can also take that entire tire scan with one of our ruler devices and still have very high resolution imagery here and still be able to pick up, some pretty decent defects and profiles from even a large field of view that we see scan a whole tire here. Going further, we can see a couple other scans. I know I mentioned treads as well, so we do have very good high level of detail as we look at a tread inspection. Being able to see into the treads themselves, looks like some defects or rocks, that might be stuck in the tread there too, so able to pick up a lot of those defects and the actual tread inspection itself. There's another one here too. Some nice full tread here too. So as we're building up these imageries, we are using a 3D triangulation. So in this sense here, the tire was most likely rotated around in front of a laser line that the ruler is projecting and making a nice linear image out of the complete scan. So we do require that motion to create that triangulation. So again, as we're doing final tire assembly, the tires are probably being conveyed. So we got tires moving underneath the ruler. For these tread analysis, we might have a tire spinning in front of the ruler. So again, ruler being stationary in both senses with the product moving in front of it. Really don't care how that motion happens, as long as we have some sort of motion to be able to triangulate and create those profiles and create our analysis here. So SICK has been very, ingrained in tire for quite a while, doing a lot of the 3D inspections. It's been a very high-end type of applications traditionally in the past, minus talking about the ease of use tri-spector, where the ruler has been more designed around those, very high-end, high-speed applications. SICK has just recently released some ease of use configuration software built behind our ruler platform as well. So we're able to actually utilize the high-end ruler and then have some ease of use customizable software behind it, to really alleviate the entry point into benefiting from the 3D high-end ruler devices that we see here. And now I want to jump just briefly into what can 2D do for us now too. I know 2D is probably not as prevalent, especially in tire when you're talking about these matte black, low contrast type of scenarios. However, there's a big push around a lot of noise around AI and what can AI do for us. So as we start to look at our inspector portfolio, we have a nice smart camera that can actually start to deploy and run AI algorithms directly on board the camera just by simply teaching it a few good example images. So in the sense here, you can see we have a nice configurable graphical interface, just a web browser interface that directly connects me to the camera. Looking at a sample of a tire sidewall here. So as we start to look at analysis and try to see what can AI do for me or what can a 2D camera do, it's really going to be good for defect detection, whether it's markings or even some measurement applications as well, where we might want to look at utilizing some of the higher res 5 and 12 megapixel imagers that we have here. But as far as what can we do for AI, we have what we call our anomaly detection algorithm. So we're able to actually go in here and say we want to train portions of the image for what we want to inspect. So nice thing about how we go about training our AI is we just have to go and take a handful of good images and we can train a network directly on the camera itself. So as I collect a few different images here, add active image, we'll do one more just because. So we have just a handful of images, and we can go and train a network. So ideally, anybody can really go ahead and set this up. So as you can see, about 2 seconds to train that AI network, and I can go and click train here, or trigger, and we see our AI region is passed as far as there being no anomalies in that region. So it's really enabling, I'd say, the plant floor level to be able to train and set up a configuration camera. Where in the past you might have had to bring in a vision engineer or call in sick to come and condition your camera for you, where hopefully anybody knows what a good part might look like or what tread A versus tread B looks like, and you can say, here's my class of tread A, here's my class of tread B. I can train that directly on the camera itself and not have to worry about downtime or anything like that because the camera got bumped or a camera got moved to a different location and now I need to retrain or recommission the camera. So as we look at here, I'm going to try to see if I can't create some defects here. As I scuff up and mess up that tire there. And let's take a new image. And we can see some of the defect, the analysis that we just saw just by scratching the tire and creating some defects in the sidewall there too. Traditionally, that had been a very, very tough application because of the low contrast, because looking at a pixel counter or anything that's going from variations of slightly different grayscale, it's gonna be very, very difficult. Or now we can utilize some AI and actually do some simple defect analysis on a tire assembly, even with that low contrast. So thanks for joining us today. If you'd like to know more information about what I talked about today, you can visit sick.com, email us at info@sick.com, or you can reach out to me directly at the contact information below. Thanks again.